Car of mass 1,500 kilograms goes over a hill at a speed of 20 meters per second. The shape of the hill is approximately circular with a radius of 60 meters. And by the way, too, that 60-meter figure, I got into the West Virginia Highway Department website and looked at how they design roads. And in Colorado, we don't have hills that do that kind of stuff, but in West Virginia, they do like nobody's business. And they cut the roads so that they have these arcs of circles. And so that's where that number comes from. It's a real figure that you can have on certain kinds of roads. Questions: what is the force of gravity? What is the normal force of the road? What is the fastest possible speed at which the car could move? Here's how we'll solve this problem. We're going to solve it exactly the same way as we've solved all the other force problems. We're going to tell two stories. We have a motion story to tell, and we have a force story to tell. And what we're going to do is this. I'm going to do a side view of the motion that's just as drawn right here. Okay? So the motion is in a circle. Car's moving like this. Velocity is in this direction. Question: what's the direction of the acceleration on the car at that instant when it's at the top of the hill? Straight down. And it's straight down because it's towards the center of the circle. It's towards the center of the circle. And I can also say A is equal to V squared over R. Okay? A is equal to V squared over R. Now, let's look at the forces. And for the force picture, I want to do exactly the same picture. Here's my side view. Here's my car right at this instant. I'm going to look at the forces which are acting on the car at this instant. Weight force, and it's down, and the magnitude of that is equal to, how would I calculate the weight force? Mass times G, M times G. Excellent. Okay? And there better be one more force, normal force, which acts which direction? Bigger or smaller than the weight force? We just answered that in the previous slide. Smaller. Okay, so we got that. So the net force, what's the direction of the net force in this case? Downward, because the weight force is bigger than normal force, okay? So I'm going to write this. The net force is equal to the weight force minus the normal force. I'll write it that way, and it's pointing, and it points downward. That's my net force in that direction. F net is downward. Oh, and the net force is also equal to mass times acceleration. Oh, yeah. I think we're making progress here. Now, let's go ahead and put some numbers. First off, what is the weight force equal to? Well, weight force is just mass times G, 14,700 newtons. And now we need to find the normal force. That's the next piece that we're asked. I'm going to put a question mark there. Because how big the normal force is depends on what the acceleration is. Oh, but I know what the acceleration is. It's just V squared over R, right? Let's go ahead and calculate it out. For this particular problem, the acceleration is equal to 20 meters per second squared divided by the radius of the circle. And the radius of the circle, we're told, is 60 meters, okay? So that's my acceleration is. Normal force is equal to the weight force minus m times a. Weight force, 14,700 newtons. The mass of the car is 1,500 kilograms. And the acceleration is 20 meters per second, all squared, divided by the radius of the circle, which is 60 meters. And so I can put all those numbers in. Everything's good. And I get a number of 4,700 newtons. And we said it should be less than the weight force, right? In fact, it's quite a bit less than the weight force. It's quite a bit less than the weight force. So I'm going to talk about feelings for a second. Can I apologize for that? I know we don't do that in this class. If you're doing this and you're going over this rise in a car, remember we said you don't feel your weight. What you feel is the normal force. So if you're riding and the normal force of your seat is pushing up on you, all of a sudden the normal force on you gets less. And so you feel lighter. You feel lighter, okay? And that's that idea of apparent weight. We'll have more things to say about that on Friday, okay? Now, next up, we're going to solve for this question. What's the fastest possible speed at which the car could move? Now think about this. The car was going at a certain speed, and the normal force is less than the weight force. What would happen to the value of the normal force if the car speeded up? What would happen to the value of the normal force? It's going to decrease, because the car goes a little bit faster, which means the acceleration is a little greater. And our equation for the normal force says the normal force is equal to the weight force minus mass times acceleration. Acceleration gets bigger, normal force gets smaller. What's the smallest value the normal force could have? 0. 0. All of a sudden, like the car's tires are like, they're just touching the ground, but they're not pushing against the ground, okay? And that's as fast as the car could go. What will happen if it goes faster than that? It's going to catch air. I mean, if it goes faster than that, it's not going to go in a circle of radius 60 meters. It's going to go in a bigger circle than that. And so the car is going to like leave the grounds. So let's assume that you don't want to do that. Let's assume that you don't want to do that. Then the problem looks just like we've seen. It's like this. Here's my car. And it's going at a velocity v. Acceleration is directed towards the center. Acceleration is equal to v squared divided by r. But the forces, if the car is going as fast as it possibly can, there's one force acting on the car. What is it? Weight. That's it. And so what is F net equal to in this case? Just weight. F net is equal to m times g. So m times g is equal to m times v squared divided by r. And so v is equal to the square root of g times r. It's just the square root of the free fall acceleration times the radius of the circular arc. And if you do that, you get a speed of 24 meters per second. 24 meters per second is just over 50 miles per hour. So if you look at like websites of road designers, you can have a hill which has a radius of 60 meters if it's on a road where people aren't supposed to go faster than 40. Okay? You go over it and you feel like, you feel that little, but you don't go airborne. Okay, if you put this on a road where people are driving 65, people are going over the rise and they're like catching air every time. That's not a good thing. That's not a good thing. Because when your tires aren't touching the surface of the ground, you got no normal force, you got no friction, and you're going to go in a straight line. Yeah, that's not so good. So you don't want that. In fact, they build them that way. Now, there's also specifications for the dips, too. There's specifications for the dips. Because when you go through a dip, your acceleration's upward. Okay? The normal force is bigger than the weight force, just like the ball on the string. And so you're going to get pushed into the road. And you don't want people to be going through there and being like, you know, feeling like their apparent weight is like triple or quadruple their actual weight. You don't want that. You don't want that.